Okay, we are live. Hello, Internet. In this episode, we will focus on the parsing of theorems, which would look like the following. The syntax is something like that here. Theorem, it's like the keyword that starts the theorem definition, and then you give it a name, and then you would write equal sign, and then an expression, a theorem expression. A theorem expression always starts with an existing statement, like an existing axiom or theorem. Let's say that we have some axiom defined before. Let's say that we had my axiom 1, for example, equals whatever it was. Okay, let's write something more beautiful. A and B makes C, for example, whatever your axiom happens to be. And then to start a theorem, you would start with choosing an existing statement to start with, like for example, my axiom, and then write all the moves that you want. You can write them in one line if you want. It's like JavaScript syntax, like C-like language syntax, almost without the semicolons. So dot means access an operation, call a function, access a field. Functions will have parentheses, so the syntax looks very much like actually the language that we were writing that in. Like it looks like Kotlin, honestly. And the challenging part is that new lines should not really matter. You should be able to do that. Call a function and then call another. But you should be able also to do that for readability reasons, of course, like when we have a call chain, obviously also probably in our source code as well, we would find something like that. It's much easier to spread it into multiple lines. Actually, I don't find a change statement weird. Okay, but I guess you know what I mean. Where are we? Here. So breaking the multiple lines obviously will improve readability. So our parser will be able to handle this. The thing is that, remember, we cannot completely ignore new lines, right? Like that should not be allowed. Here, a simple space does not end the command. To end the command, you have to put that into a new line. So the new line has some power. So the challenge for today would be to sometimes tolerate new lines and sometimes not. For example, if we read a new line, or multiple lines for that matter, and the next token is a dot, we understand that this is part of the expression that we are already parsing. If it's not a dot, probably it means we have a new statement and we have to roll back the token and return and say we parsed our expression, here it is, we save it with this name, and then it's the end of the theorem expression, so to say. So it's our terminator. Also, end of files can at any time. Here we could find the end of file here. We should be able to handle this. So yeah, it's gonna be a little bit challenging, but I'm pretty sure we will make it. Now, let's talk about the properties that an expression can have. There are about 8. I think I had those in the notes. Let me check. So, it was, let's close that. It was here. Sorry for that, I should have it ready. MathAsm, where are you here? Notes. So, here it is. Right copy, we would have left copy. We will explain what those do, but for the moment, just assume that there are the operations of MathAsm. There are about 8 of them. So we have right copy, left copy, replace all, replace on the left, replace on the right, replace 1 on the left, replace 1 on the right. That's it, 7 operations. With those 7 operations, MathAsm claims, at least that's the idea, that you can take any set of axioms and prove any theorems that derive from those axioms. So these 7 moves to replace symbols in an existing statement with other symbols will be the mechanism through which we will prove theorems, basically. We replace symbols with other symbols, and this way we come from a statement A to its proof, let's say that's a statement B. And in the meantime, we can use any theorem or any axiom that we have already proved in our theory to advance the proof of the theorem that we're currently proving. So old statements can be used in new proofs in a sentence. This is how it's going to work. Okay, let's start with this then. Let's go to the theorem parser and create a unit test for that in case we don't have already one. No, we don't. So, sorry, no, we don't. We test those guys through this guy. I don't want to break the unit test too much. I want to test this guy end to end, and whatever internal complexity this guy may have, I don't care. I create those files only not to make this class too long. But in fact, I consider this as a module and I want to test it as it is as a whole. So we have already a test for that. And now we will, let's run all of those, by the way, just to check. And we don't need that one anymore. Just let's take this together in our unit test, basically. Let's put it here. Our notes, we will probably remove them at the end of the day. And also we said we make a git branch on every episode. Good. So let's make, how we name the other one? Git branch, let's stay consistent in our naming conventions like that. Okay, git checkout -b, episode 3. Right, nice. And the unit tests all pass, great, we're good. So let's create new test and write should parse axiom public. Should parse 3 axioms, public axioms. What? Should parse 2 axioms. That's the name of that test. Should parse simple theorem. Let's see how this would look like. We would have something like that. Theorem, my theorem is equal to not quotes, axiom 1 dot right clone, for example, or right copy. Let's call it right copy. And let's parse this thing. Oh, sorry, we did it already. Parse string, and then we expect to have one statement. We expected to have name, get name is equal to my theorem, and of course this would fail completely because we don't have done any of this at the moment. So let's send 1. Of course, we just reach our to do, which is a Kotlin way to say just throw an exception with this message, which is a nice feature actually. And here we are. So at this point, I assume we have parsed, okay, the name. Let's make a breakpoint actually. Just get a breakpoint here. If they need a command, no, we can put here. Nice. Okay, so let's debug this. We have actually parsed the identifier, which is the name of the theorem. We have parsed the equal statement. Not implemented, yes, of course, not implemented because I forgot that. So, and we need to return something, right? No, we don't. Why we do? We don't return anything, do we? Of course we don't. We don't need to return. Okay, so let's debug this and see what is the next token we get. So the name is correctly parsed. Let me close all the relevant tabs and just keep the theorem parser and our unit test. Actually, we can even do it like that. You know what? I prefer the test on the right, on the left. And let's put the other guy on the right. No, it doesn't want. Split right. Thank you. So here we are. We have parsed this, and we have parsed the equal sign, and then we should parse an expression. Actually, we should say parse expression, and this will be probably a recursive function, because you can, inside that expression, you can have sub-expressions, like here, for example, other theorem dot all whatever. So this would be on itself exactly the part I highlighted is also an expression, but is also a part of a bigger expression. So all of this process will be executed again and again and again, and the result of this would be a MathAsm theorem, expression result actually, which is a statement. Resulted statement. Statement meaning a theorem or an axiom. This is basically what we get when we parse this. And yes, we need this to be a MathAsm statement. And now we will create that. And after, we will have to define that statement. Now we don't need that. Or you know what, for clarity, leave it. Sometimes it's not so easy to understand from that. So it's a MathAsm statement, and we just define it. And then we are done. Maybe we have to stabilize it. I will tell you exactly what I mean afterwards. Stabilize it. Because for efficiency reasons, for performance reasons, some of those statements will be mutable. Because of course performance is crucial, because we are building a parser which can parse multiple files. Maybe some mathematical theories will be megabytes or gigabytes to parse. And such things will make a difference. So we can reuse some objects on the background while we're performing all those operations. But once you define it, it should be read-only to avoid inconsistencies that MathAsm would not really allow for. Like, those things are immutable. Once you define them, there is nothing mutable about them. And thus we would need to here really clone the arrays, clone the lists, and keep them strictly read-only. And then define it, and then we are done. The million-dollar question now is how we parse expressions. So, first we would start with an identifier, always. Tokenizer require identifier dot name, and then we would need to resolve that name. This name refers to an existing axiom or theorem, so we will say, you know what, I want to rename this thing. This is the parsing context or environment. Let's call it environment. Yes, please rename all the parameters. This name was stupid. This is what I meant. I will explain what this object is. Just select all, yes, and refactor it, please. Nice. So this will define the actual business logic. What does it mean to define a statement? Do we save it maybe in a database? Do we maybe just keep it and print it back to the user? What we do? The parser should be, of course, agnostic of such details. You could parse and do anything with the result. So you need somebody to be above you and just tell you, hey, I parsed a theorem, do whatever you want with it. The parser simply reads the file and produces the result. And then what we do with the result is up to us. And this context would also give statements to the parser. And we would need things like get statements. Okay, this is get all. This we call at the end. And we need a get statement by name. And it returns a MathAsm statement. Or it throws an exception. If the statement is not found, then we should throw an exception, so we don't make this nullable. Now we will call that and say, okay, statement start is the, let's call this env. Env get statement with name. And the next thing we require is a dot. So from here, the valid options is we find the dot. And here is where we should skip new lines. So between a name and the dot, we are allowed to have empty lines. So the first valid option is we find the dot. The second valid option is we find another statement start. So important, allow new lines, but remember if you met any. This would be important. So the first thing is that we find the dot. The second option is we find something that is not a dot. But we have met empty lines in that step. This would be the case where you write that. My theorem is my axiom. Bird, not now. Yeah, the bird is very happy. Okay, so one could write this. This is valid MathAsm. So my theorem is my axiom. You basically make a copy. Just you reference the same variable. You say a new theorem is simply the axiom. It changes nothing. It's completely useless, but you can do it. The next thing which you will find is the new statement. Can be a theorem declaration, can be an axiom declaration, can be whatever. It's the new statement. The question is, if between here and here we met a new line, then we say, okay, we gracefully terminate. Here is the new statement, so we did our job, and that was our mission accomplished. But we have also rolled back the token. So the next statement, parser, whatever it is, will start from here again. Second option would be to have a dot and continue. Third option would be to find something that is not a dot. That's going to be the illegal scenario. We find something that is not a dot and no new lines were encountered. So, in that case, we throw. And why we throw? Because imagine if you see something that is not a dot, it means it's another statement. And okay, let's put it here. So this would be that option. You didn't encounter any new lines, you just found this token, the identifier, and then a new action declaration or whatever. This is not valid MathAsm. We don't have semicolons, but you have to put a new line to start a new statement. That's why it's important to remember if we skipped a new line or not. If we skipped a new line, then it's fine. If we didn't, then we should throw. The syntax should not allow that. Okay, so we got the statement start, then the question is now, next token is tokenizer. Tokenizer dot require identifier. No, we require whatever actually. Next non new line. Yes, we have to create a function about this actually. Let's create a function about this. Private fun get next non new line. And this would return a data class that will say what is the next token I found and if I skipped new lines or not. Because you remember we need both. We need the token and the information. So we can call that, let's call it foo for now, and let's create that foo, private data class foo, and we have next token, which is a MathAsm token. Yes, Val, thank you. And we have the encountered or skipped lines. It's a boolean. Skipped new lines. So token with lines result. It's a stupid name. Token with trailing lines. Let's call it that way. Trailing is before or after. I always confuse this. I think it's before. Yes, trailing lines. Okay, so first you see the lines and then you see the token. So let's put it in that order. So we get that. We will see what we do with this, but in any case, we get the next token. And then we say, if it's a dot, you get a new identifier. So you have an access, it's a field or it's a function, but you access. So what you would need to do, and you can have many dots, So probably the whole thing should be in a while loop. Oh my god, that's difficult. Okay, let's enter a loop. Let's enter a loop. I think it's unavoidable. And the statement start probably. So next token dot token result. Let's call it token. If the token is a dot, then continue basically. If the token is a dot, no, you don't continue. At this point, like when you enter the loop, you just parsed an identifier. This is how we enter the loop. And after the identifier is the dot, and then you read the dot. You read the thing that's after the dot. After dot, we will find better names for those guys. This tokenizer command. Next. Here we don't care about new lines. Like after the dot, you have to write something. And now the question is, what is the next? It must be an identifier actually. Require identifier. Field name. Let's call it field name. And now we have, of course, to execute the field and get the new statement. Well, new statement is this dot execute field. It's not really execute field. Parse field access. Member. Let's call it member, because it's either a field or a function. We call those members. Parse member access. So let's call it here member name. It's like an object-oriented programming concept. Let's use the same vocabulary since we are familiar with it. Okay, so you know the member name and parse it. And you return, in any case, MathAsm statement. Our language is easy. It doesn't have numbers and booleans, and it has only one type. It's all MathAsm statements. There is no other type of expression. Okay. So we get the new statement. And then the next thing, we are again here. We either have a dot or whatever. Like, imagine that we would do that. We pass the dot. We pass the identifier, like for example invert, and then we can say clone, left clone, for example. So we pass the dot, bird. Why now, bird? We pass the dot, we pass the identifier. The next thing that we are expecting is again another dot, or the end of the statement. Both are fine, like we could be in that case. Or end of file. Aha, good. End of file is also legal. So let's write here. End of file is allowed. So you know what? Let's make a one statement. Don't annoy my viewers, which I don't have any, but still don't annoy them. Okay, so token result when this is a dot. Dot token, of course. then we do that. And when it's an NO file, we just break the loop, I guess, right? So what else do we have? We found the dot. This is handled. It's not really handled because first of all we have to pass the statement, the existing statement actually, which should be a var. For that reason, sorry for that, but it's the only way. And here is where we reassign it. So for chaining, we say we execute this dot and our existing statement. This is kind of the this of the expression, like what is behind the dot every time. So in the beginning, this is the this. So we say my axiom dot invert. So we execute the member name on the statement. But then the result of our expression is another statement, in which statement we will call dot. Like it's like Java, it's like reading JavaScript. It's exactly the same concept. So we need to have this mutable. I don't like I try to avoid mutable state at all costs, but I think here it's pretty much unavoidable. So pass this parameter there and write target. Actually, is the thing behind the dot. Target object. Let's call it that way. And that's a string. We don't care about member names here, so dot name. No, dot name. Let's write it here. Why not? Okay. And then the loop continues. So we can be a dot. We can be an end of file. Else. Anything else does the following. If we did not encounter any lines, we throw. Unexpected token exception, and we need to put that in another class. And we say end of line expected before statement start found token result token. Else we need to roll back this token, the token we found, and break. So this .tokenizer.rollback token, we don't have this yet, but we need to create this function, and then break, or even return, I would say. Return, let's say current target. Let's call it that way. Return the current target, and here actually we also need to return the current target. Else here. Not really a fan of writing code like that. Like, this function looks complicated, has too many nesting levels. like 1, 2, 3, 4. It's not nice. We have to find a way to make it simpler. So we can put maybe that here, that function. So instead of having this, we need to return the next one. So if it's a dot, current target is this dot parse member access of the current target. So this, at least this complexity, and then let's write private handle statement end, or handle, yeah, statement end. I think it's good. So we need the token result, which is this one, and we don't return anything. No, we do. Actually, if we do need to return something, it's only for cosmetic reasons. So we could say this dot handle statement end, and then say break, or actually return current target. We could do that, but it's gonna be nicer if we could do that. And this means giving an extra parameter. Yeah, let's do that. Parse expression. No, what you are talking about? Here's a MathAsm statement. Yes, make the return type here. No, not that return type. That return type. Yeah. Which now our function looks a little bit better. So now it's almost clean, almost. So every time we find a dot, we keep parsing, and if we encounter end of file, which is kind of also a kind of statement end, I have to say. So we could even handle it here internally. But let's say we can consider it kind of a special case. It's no real deal. And then we do that. Okay, it seems good. Now we need to only parse the member accesses, and at the moment we will make something very dummy. We will simply keep returning the same thing. So we read the member name, but we completely ignore it and we return what we give back. So here it's a to-do from our side, but it's still working. And I would like to implement that now and say while true, while next is tokenizer.next, and if next is a new line, end of line. Maybe if it's not, return it. So if it's not the end of line, return the token, and this of course should not be false. Let's see, we need again a immutable variable. In the beginning it's false, so we just return that. You know what? I don't like this order finally. This works better for the constructor because this sounds more natural. Yes. The token and then the lines. Okay. Else, okay, we don't even need to write else actually here, just skipped lines is true and keep going. I guess that would do it. And finally we need to implement the rollback mechanism. Oh god, that's... Okay, we have rollback characters, which is an internal thing of the tokenizer, but... we have to somehow roll back this token. It's a little bit dirty what I'm going to do, but rolled back token, MathAsm token is null. And the first thing that next would do is if that's not null, you do nothing and you just return it. Okay, we need that. Yeah. And this should never happen, by the way. Like, we should never even need to do that. Okay, yeah, let's forget about this. Else, okay, this should do the trick. Here we roll it back, and here we say the first thing we do is, if you have it, give the rollback one. If not, continue doing what you do. And each other function calls that, so we will be consistent. So everything goes through that except that guy. But that's a completely different. You don't even ask for a token here. Which means that this guy here doesn't really fit in this class. If we extract him on another class, what we will miss? Aha, the next active char. This is pretty damn important. Next char. Rollback. No, it's very hard to decouple him. Okay, forget it. So, actually, you know what? The definition should stabilize it. Let the stabilization be part of that guy internally. The environment should do it. But when they define. Okay, so member name is. Now we execute an member access. Okay, let's see what we do here actually to see if we fall into some infinitive loop or something. Because we should get this working even without executing this guy, I think. So, it tries to get the statement. Good. It tries to get the statement. That's great, actually. That's great. We have to find a way to mock those guys. Yes, we have a mock here, don't we? Let's see, let's write function, helper, private fun, define axiom, name, just define statements, add MathAsm axiom statement actually. How did we call that? Let's go to axiom parser. We call that guy MathAsm axiom. So name, left side is list of A, B, and then it's list of C, doesn't really matter, and then is bidirectional is true, and then weight is 2, and that's it. Okay, let's see. Well, axiom is that. This will save us one line of code if you count the parentheses, because we can do it in 2 lines instead of 3, and I like that. So here we say this dot no, what are you talking about? They're talking about this define axiom and define the axiom with name axiom1. So this axiom exists. We could start really mocking methods instead of finding this trick. This is not really a mock. We just say, hey, pretend that you define your statements here. But it's also okay. It's also okay. Okay, so let's see what we do now. Can we parse this thing? No. Get statement. Yes, of course, of course. Actually, this is kind of, it's not really a mock, it's like test implementation what we do here. Okay, so I'm not sure if I'm happy about this. We will think later. So find it dot name get name is arg1 arg0. What's the problem? No. returns no. How can we do it in the mock? Answers this dot result. Oh god, let's see that. Mock k answers call original, no answers. That's the okay, yes. Yeah, I know. Okay, I know. It's simply that it's nullable or throw null argument exception, whatever. Doesn't really matter. Yes, now it will get the statement. Okay. Expected 1 but was 2. Yes, of course, you're right. So first we define the axiom, and then actually the first is the axiom. We don't even need to test that. That's not part of the test. So first we define the axiom, and then we define the theorem. Okay. Let's debug here and see what we get. Not here. Here. Okay. On this stage, the result has two statements inside, which is good. We get the axiom 2 times. Of course. Okay, I see now why. We completely ignore the parsed name actually. After we parse the final expression, we need to also use the name somehow. So when we say parse exception, the first thing is that we get a statement which we have to clone with a new name. So the expression with which we start will always have the same name. Okay, now the question is who should clone that? The environment should clone that. Yes, this get statement should accept two parameters. The statement that you want to get and the name that you want to name your expression as. Or should this be the responsibility of that guy here? No, let's make it of that guy here. So clone would be here. At some point we have to clone this. We could either do it here, or yeah, maybe there would be better. In any case, you stay here. You don't inject that. You don't clone that here. We clone this at the end. So definition is clone name, and define the definition statement to define. Yes. And statement to define. Let's get statement to define. So, return MathAsm, not action but theorem. We would create that class. Okay, now we need to create some new files. So we have the axiom, and we will have the theorem. So MathAsm theorem would have a name, of course, left side, right side, yes, every one of those. Is axiom false? Is public? Is public. Here we will need to actually store that each time. We have public theorems which we export to theory, and private theorems that are just intermediates that we use internally for the proof and nobody cares about from the outside, so we don't export them. So that's gonna be a hint for the parsing environment. Okay, we have the left side, we have the right side, of course, we have the weight, and we have the bidirectionality. So, okay, we create one of those guys, and now name is the name, of course, and left side is the get left clone. Copy. How do we make a copy in Kotlin? Slice. Oh boy, really? I don't know that? I should know that, guys. That's embarrassing. Kotlin list make copy. It's a mutable list. Okay, but I return an immutable, but nobody cares. Okay, so let's copy that to be extra sure that we stay completely mutable. Right side is that to mutable list. I'm not completely sure if maybe I'm paranoid about this. Maybe we can guarantee that we don't mess during the process. But here, just to be extra sure, I clone that before defining it. Maybe we remove it later if we think it's not really necessary. So is bidirectional, we just get that from the original. Weight again from the original. Weight is original, get weight. And is public at the moment true, and it is a to do from our side. We need to also support private theorems. Okay, so nice, we do that. And now let's see if our test passes, because now we should use the new name and the resulting statement should be called like that. Let's see. Okay, we don't need that. Nice. We parse the theorem. Should parse theorem, that's right, ending. Okay, should parse simple theorem. No, let's leave it like that. Should parse theorem ending in new line. Let's see. We should have a new line. Again, we should have my theorem. Okay, let's do the following. I would like to save some code. Existing axiom name. So just I need to make this guy always being executed actually. So no, not that. Here, define action. So we need to make this an extension function of that guy. Why? Because I want to chain it like that. Parsing environment. Sorry. Parsing environment. Parsing environment. Good. So, yeah, we don't need to write this every time. We know we have an existing axiom. Let's run all the tests and see if we are moving. So now this should also, perfect, we destroyed everything. Yes, because we actually test the sizes. Yeah, that was a bad idea. Okay, I admit it. It was a very bad idea. This and how it's called? Our mock executor, no, and E and V environment. Okay. Yeah, in this case we don't even need the constant. Yeah. Okay, yeah, that was a bad idea. Forget it, revert, bye-bye. Let's see if we handle theorems ending in new lines. Nice, we do. Now we need to see if we handle dots. Should allow chaining, expression chaining in new lines. So we should have a new line here. Actually, let's write it like that. So we don't need that, we don't need that, we don't need that, we write like that. Should again be able to parse that. Nice, and we should also make sure that here the end of file was found. But no, it's fine. We're parsing one theorem. No, it's okay. Let's make it a little bit more difficult. Okay. Nice. Now we need to actually execute the commands. So we recognize specific commands. Right copy, left copy, invert, right, invert, yes. All right and left. I think that's all the things we allow for. If it's right copy, return this dot env dot clone right side of statement. Target object, actually, call that. That's it. And if it's a left copy, we return clone left side of that. If it's invert, we return the invert of the target object. Invert means take the two parts and exchange them. So if you have AB makes C, the inverted version of this would be C makes AB. Just flip the left and right part. Flipping is only allowed for bidirectional statements. You cannot flip a single directional statement for obvious reasons. Trying to invert a single directional statement would throw an error. Actually, it's a semantic error. Okay, all would be, hello Cookie. All would be replace all. Yeah, but replace all with what? Here we need the base of the operation. So unfortunately here we need to parse things. Okay, so private fun parse parse replace all. So we return a MathAsm statement. So here we have one to do. I promise you it's soon gonna be over. Like, there are not many options that MathAsm can parse. So here we say replace all, and here is replace left, and here is replace right. Yes, we need the target object. Nice. And here, and here. So replace right and left. Else throw unknown member exception, and let's give the member name. Yes, please create that. Yes, please here. What is that? That's part of that. Okay. Runtime exception, and let's give the message member unknown member. Please use, yeah, sure, dot all. No, we don't need examples. It's not the job of the parser to teach MathAsm. Okay, now we have this is our top level function. Yes, please move it inside. So we have the name, and no, you know what? I liked it more like that. Disable inspection, that's stupid. Sometimes it's nice, but giving it a name makes it, I think that's more easy to read, in all honesty. So return target object, yes, we'd never do that. And now, of course, our unit test would fail because we would actually execute that code and we would throw all those to-dos. And we should start actually implementing the parsing of what happens. So in all cases, first of all, tokenizer require an open parenthesis. Parenthesis open. In all cases, we would do that. So that's a starter. And in parse all, it's easy. Is this dot parse expression actually, and then we require a parenthesis close, and then we return this expression. No, wait a minute, that's we return replace all target object and base. Let's call this the base of the replacement. I will explain what I mean when we talk more about the actual rules of MathAsm. And let's say target, and here is the base. Yes, and we need that in all the replacements. And here, and here, but without that guy. So, we parse the parenthesis open, we parse the expression, we parse the parenthesis close, we make the replacement, we return the result. That's perfect. Now, pretty much the same thing is gonna be done here, with the difference that we replace left. Yes. And here is where the thing is gonna differ a little bit, because for left and right we have some extra possibilities. We support two syntaxes. One syntax is to say, we will do that later, with one parameter or with two parameters. The all function always accepts one parameter, but the left and right can support a version of one parameter or two parameters. So we actually need to parse the expression and optionally a number if it's separated by comma. And this we're gonna need to put in a separate function, and that's why we need also a data class, and we say replacement parameters, and we need the expression, the base actually of the replacement. It's a MathAsm statement, and we need the second parameter is the position, and it's an int, maybe it's a nullable int. Actually, you know what, these are small and cute enough to do that. Okay. So we need private fun parse replacement params, and we give that back, and we do something like that, but not quite. The difference is next, and we say when next token is a dot, not a dot, sorry, if after the expression we find a comma, we keep parsing, okay, let's do the easy part first. If it's a parenthesis close, we just return this one with a base that we read above and no number, so null. But if we read a comma, then we return actually, okay, we say the number, position is tokenizer require number dot value, and then we require parenthesis close, and then we return the thing in the correct position. Else throw unexpected token exception. What message? Expected parenthesis close or comma. Okay, so in that case, the parse left is replacement parameters params. Yes, we parse the replacement params, and then return if position is null, return that, else replace one single left, and we need the position. Something similar would be for the right side. Replace right, replace single right. And I think we have all the operations. We have, okay, the public, not public axioms. We can, of course, theorems, the public, not public theorems. We can speak about that. But at the moment, I think we are good. Let's see. Of course, now the things will fail because we don't mock the actual operations, but we will very soon. So we will have here, let's say here, allow replacements, or allow proof operations. So we will say every replace all returns argument 0, right? Any. Just return the target object. And then we need to replace left again and replace right. Now we need the replace single left. Whatever the arguments happen to be, we always return the original target. And we need the clone right, clone left. Okay, clone left side off, clone right side off, and here we need one parameter, actually 2 parameters less. Okay, and it's not proof executor. Now we say that file is called proof parse environment, I think, right? Yeah, parsing environment. Parsing environment box. So here we would say that we also allow proof operations. And here we would say that we allow that, and also here. And then we have to verify that those methods were called actually. I think we're in a good way. We have of course, the invert. We forgot the invert, obviously. That's also an operation. Invert, okay, let's put it invert. Any, just return the argument. Let's see. Oh boy, that Earl Grey is perfect. It's really good. Okay, it seems like we are in a good way. Now, I will start testing that the actual operations are being called. And, okay, should, let's say, should perform write copy. And then verify this.end, okay, env. replace not replace, clone. Okay. We can keep it that way. I hope that's fine. That's first, like that. Nice. Left copy. Yeah, sorry. Clone left copy, left side of that. Nice. What else should we be able to do? Okay, right copy. We should invert. Should perform invert. Invert. Should perform replacement, replace all operation, let's say okay, let's define two axioms here. Actually, we could even make sure that the parameters are the correct ones. So we get here a theorem of that name and then a theorem of the other name, but I guess we can write other unit tests for that later. Now let's make sure that all the operations are supported. Okay, this fails. Why does it fail? End of line expected before what? Here it seems we found the parenthesis close, and why you wouldn't expect to find that. We roll back something that we shouldn't. So the parsing all does not work good. Okay, we require that, and then who is calling us? Sorry, no, wrong. Parse member access. So we found the identifier, parse replace all. We do that, we do that, we do that, and then I don't understand where the problem is. We don't even come here. Okay, because we parse the expression. I see. The end of the expression here is expected that our expression ends with a parenthesis close. That's legal. even with a comma it would be legal. So parse expression should not throw, it should return the token. And the caller should decide what to do with that. But it already returns a value, so we have to create again a wrapper object to create both. To create, hey, I parsed the exception, here is my exception, and here is the last token that made me stop. Okay, guys, sorry, I have to make a break for a single minute. We can make this work, but we have to complicate this expression a little bit. It has to return two things, the token and the statement. Okay, so I will play you some music until I'm back. I will be back in 1 minute. So, I'm gonna play some Mozart today, since we're in Vienna. You don't eat my laptop while I'm gone, okay? Don't eat the laptop. Promise? Promise? We will see. They didn't need the laptop. You're the best birds ever. Tilly, may I sit? Tilly, may I sit on the chair? Okay, Tilly. Sorry, but I must. Okay. So, let's move. Thank you, Mozart. We close that. We need to somehow return to things, but we already have a rollback mechanism. So I guess we can simply, if we see a statement end, we can simply roll back and return. So we remove that completely and we say the following. This tokenizer rollback token Actually, now that I think about it, this would be simpler if it's gonna be an if-else. If it's a dot, then do that, else do that, and we spare one brace. Better. Simple if-else clause. And here, parse expression, and then this dot handle statement end, and we don't need that. We don't need to return. Actually, we can rename this method to assert statement end valid. And we will get, we don't need to roll back here, actually, do we? Wait a minute. Yeah, we roll back in both cases. No, that's not good. We need to handle here also the case that we met a new line or not. Else, if token result skip new lines, then do it. Else, throw that. Yes. So now we just assert that the end of the expression is valid, which we don't even need to do, because I think we already have a guarantee that the end is valid, because otherwise we would have caught it here. Okay, I think that's enough. Okay, let's press the magic button and see where we are. I think, yeah, we have hacked it. Which test is failing? Parstring. And we throw end of line expected before statement start. But which test? This one. End of line expected before statement start. Ah, yes, of course, we have to. end of line, end of file should be allowed. Yes, we have to put an else if here. Else if token is token is end of file, then you don't even have to roll back, simply return what you have. Okay, that's better, but still we don't parse the parentheses right, because here end of line expected before statement start. Yeah, that's the thing. That part that part should probably be done here. But how do we know that there? Where are we? Sorry, I lost now. Here. Okay, we parse the expression, and how the expression ends. It can end with a dot in case we just continue. We can end with an end of file. In this case, we simply return and say thank you. We can end with some random token that had lines in between, so we know, okay. No. Do we want to allow empty lines everywhere? For example, if we have something like that, can somebody put lines here? Maybe we're too permissive with the new lines, but we will see. If we can afford it, we can do that. Okay, and then we say it was neither of those things. It was neither a dot nor end of file, nor I found new lines. I just found an unexpected character, in which case we simply roll back and return. We roll back and return. But here we also roll back and return, and still we need to distinguish between those two cases. Between I found new lines and I didn't. Like, what's the difference? Here it's a valid end of statement. Here maybe it is, here maybe it's not. We're not sure about this case. So I think it's unavoidable. We have to return to things. We roll back the token, but we don't roll back this information here. And this information is important. Oh boy. If we could only roll back this information too. Maybe we have to roll back multiple things. You know what? Roll back tokens. Let's make a stack of MathAsm tokens. And mutable. How do we make a stack in Kotlin? I've never needed those things. Kotlin stack array deq dec push 1 2 3 4, and then you say pick, and then you say pop. Okay, got it. Array dec, it's a val array dec of MathAsm token. So here is, but pop throws, right? Pop last. What happens to that? That throws, right? Remove first. Yes. Okay. So if that is empty, is not empty. If it's not empty, return pop. And then push here. Rollback token. This rollback tokens push. Okay, let's play with the stack. So we roll back the token and we roll back a new line, an end of line. Here we just roll back the token without the new line. Okay, in that case we would do something like that. If it's a dot, continue. If it's not a dot, did you skip lines? If yes, roll back a new line and the token, otherwise roll back only the token and return in both cases. Okay, and now we call that from 2 places. 3 places? Really? Where are the 3? 1 is here, 2 is... yes, of course. Okay. Here we need to verify assert statement and valid is valid. So here we need to check if the end of the statement is valid. And we say is this dot tokenizer next, and when next is a end of file, line or end of file, then it's all good. I think that's the only 2 cases where we excuse a valid end of expression. Let's throw unexpected token exception. Statement can only end in end of file or new line. Found next. No. Yes. Okay. And here we really require the parenthesis close or whatever. Bert, what did you do there? Bert, that was not polite. You know? Yes, oui. Tell that to the camera. Tell what did you do? You don't tell. Bad Bert. Okay. Let's see how much did we fuck up. because we definitely fucked up something. Nothing? All green? Why? That's suspicious, but it looks like it's working. So here we verify that we parse the all operation. And what replace all? That should be after the... Wait a minute, do we have this left copy 2 times? Right copy, invert. Invert is not a copy, first of all. Oh god, I must be more careful how I name my test. Sometimes I just copy paste and I'm not careful. Okay, bird, I don't trust you. What do you do there? Don't bite things. Don't bite things. Sometimes she bites things that are toxic to her or not safe, so I have to take care of her. She's extremely, extremely naughty. You cannot imagine. Sit here. Unfortunately, I lost another one. I'm not sure what did it chew. I suspect it was wall. It was chewing the walls. And the paint of the walls have toxic material, so they are very, very hard to manage because they are monsters. Monsters. Now, here we expect to replace all. Good. Let's move on. Let's move with left side replacement. So perform replace left, replace in left operation. Left. We expect to replace left. And the same for right, I guess. Okay. The right should also work. And now we need the replace one in left. Replace single in left. So we need that 5, for example, and then replace single left. Left. And let's put 7. Oh boy, this class became big. But okay, the methods are decent in size. They're kind of single-purposed. Yes, we don't need to duplicate this. Seems good. Seems good. Okay, now let's make sure that we can parse multiple commands. Should execute multiple operations, multiple chained operations. So let's imagine that we are parsing the following string. Come on. So we are parsing. Yeah, actually I don't care about the trim indent. Right, and then dot left, and with axiom 1 again, and then let's say right copy, and then all. So we should replace one right, should clone right of any and then it should replace all, no, replace right. Our tests are not very detailed. Normally we should also ensure that these parameters return the perfect result, but for now it's okay. We will improve our unit test later. We have to we are too permissive in our assertions. But it's a start, and we will make end-to-end tests as well. So probably in the end-to-end tests we will cover that each part of the chain forwards its target object to the next, for example, properly. Okay, so clone, and then right, and then left. The right actually should be also equals to 7. Replace single right. That's a single replacement. And that's a replace all in left, and then replace all nice. And now we should also parse sub-expressions, should execute nested expressions. So imagine that you want here to say right copy dot invert dot all axiom 1, for example. This is expression inside an expression, and basically invert that too, just for the sake of it. Okay, so let's see, we have here a right copy, and then we have a right replacement, which would happen at the end basically. It doesn't really matter for mock K, but just for our readability. So first we do that, then we do a right copy. Actually we do 2 right copies, and then we do invert one of it. No, 2 inverts, and 1 replace all, and 1 replace, yeah, so a lot of operations. Let's see if it does this properly. Cool. Our parser can parse this beast here. We are not bad, guys. We are pretty good. God, I didn't make any commits. Oh, I'm a horrible programmer. Normally I should do often commits every time I do something good and so on, but damn it. Okay, so let's say implement and test theorem parsing. So we can basically parse theorems. It's not that bad. Yes, we have the to do. We will do that. Another thing I would like to do is should execute statement after theorem definition. So imagine that we have yes, okay, we don't need that, and we don't need that. And then we have axiom other is a like 1, 2 makes 3. So we need to verify that we need the result. Okay. Assert that result.size statements that has size 3 actually. It's 1 we define here, 2 we define here, 3 we define here. We expect 3 statements, and then we expect the first one we know. We will not test our own. We will not test our own test, but the second should have a name. What's the problem? Get name is equal to my theorem should be called like that, and then we should parse an axiom, which is the other. After theorem declaration. So let's see if we successfully parse things that are after us. Yeah, okay. Seems good. Okay, and ensure state leading. Good. Okay. Let's push that, and then I don't remember how we do the single commit. Actually, it's no FF. We can do that like that. It's no big deal. Git checkout master, and then git. Of course, nobody should push anything there. So yeah, of course. So git merge, no FF, and then episode 3. Yeah, let's do that. Yep. Okay, it's not that bad. We have some progress. Our parser can now parse axioms, can parse theorems, can parse nice expressions like that here, can parse also sub-expressions like that. It can handle new lines in here in positions to just make each instruction in its own line, but still respects new lines when it should respect new lines. We haven't started to test error cases yet, which is a big, of course, a big part of a parser. It should throw errors when the syntax is invalid and should also provide meaningful error messages. At some point, we will also have to think about the cursor, because, of course, any compiler, when you have a syntax error and you click the compile button, any compiler that deserves its name, it should tell you that, hey, you have an error on this line and this column of the line. So we don't do that at all. In case of error, our parser would simply say something useless like that. First of all, we don't have meaningful toString methods. That's bad. Expected equals, but found identifier SD blah, blah, blah instead. But where? We should say, hey, line 3, column 5, this happened, like to point the user to the place. We don't do that yet, but we should. It's gonna be one of our next steps. Hello, chicken. And I'm not sure if this is gonna be our next step, like proper error messages or semantics, to start actually giving bones and flesh to the MathAsm operations. Like, what does it mean to invert something? What does it mean to perform a right copy or a left copy or replacements? We have to implement the actual operations with which MathAsm takes existing statements and combines them to generate new statements. Like, basically, in technical terms, this would mean to implement this guy, parsing environment. We should create an implementation of this guy. Not sure if we need that. Maybe not. Maybe not. We will see. Okay. Let's put those in some meaningful order. So these here are operations, and these here are environments. Like define, get, all, get by name. Let's make this explicitly. Let's see how it looks like. Get statement by name. Oh, I like it. I like it. It's more explicit. It's a little bit more easy to understand. And here I would say get all statements. And when we call that, we filter for the public ones. Okay, yes, nice. Maybe this formatting would be nicer. And maybe the environment could be injected in the constructor. It's like dependency injection. But I'm not sure. Maybe we need to generate a new of those guys each time. I'm not sure yet. We will decide that later. Okay, in any case, I will just push directly to master now. Just say rename parsing and methods. Let's push that and be done for today. Okay, we have some progress. Nice. Our parser can now actually parse things. Okay, let's close that. And next time we will probably start doing a little bit meaningful error messaging with the parser, or start doing the actual semantics of the parsing environment. One of the two, I'm not sure which I will do first. We should do both in any case. The question is what is more interesting to do first. I will decide spontaneously next time. Okay, thank you very much for being here with me, and see you in the next episode.